Okay, good morning. So let's get started. So far we had discussed that the Unix source code was given free by AT&T, and that led to many versions of Unix. So one thing that we can notice is that Unix has become extremely popular, possibly because it's open source, and also possibly it has many good features from which the other operating systems have, which were not Unix, non-Unix operating system, they have derived their features based on Unix. So Unix is very powerful in that sense, and possibly one of the reason for that it being open source, besides of course it having many good features. But the open source Unix led to many versions, and the applications ceased to be portable among the different versions, even though all were variants of Unix. The applications written on one variant will not work on another variant, and that was the origin of the POSIX. And POSIX, we had seen that it is a interface, it is not operating system by itself, it is an interface standard, and all Unix variants have to make themselves compliant to POSIX. But later other operating systems, non-Unix operating systems, are also becoming POSIX compliant, so that they become popular with the users. They can run their applications written on POSIX platforms on those platforms as well. So that was the discussion we had so far. Now let us proceed from that point. So we had said that the real time POSIX stands for, the POSIX stand for Portable Operating System Interface, and we had said that as far as a programmer is concerned, it reduces development cost and time, increase availability of hardened packages. So how does that happen? Reduce development cost and time, increase availability of hardened packages, increase ease of use, facilitated system integration and porting. So how will that happen?
So since the specification and all are now published and well maintained, so like independent developers can develop add-ons.
Okay, so basically the packages or the services developed for one operating system, one version of the operating system, can run on the other operating system. Like you have developed some application, somebody can use it on another platform also. So that's the reason for each of these. Reduce development cost and time, you can use some other pre-developed packages, increase availability of hardened package, increase ease of use, facilitate integration and porting. Now let us see the features of real time POSIX. One is that need to support preemptive priority based scheduling, and we had seen that this is one of the basic requirement for any real time operating system. And several performance metrics have been defined. The performance metrics are in terms of worst case execution times of various system calls. So all the system calls are supported, are listed, and what is the worst case execution time for them to be real time POSIX compliant are mentioned. Support for static real time priorities. So we had discussed real time priorities and had said that that is one of the basic necessity for implementing EDF or even RMA or even EDF, right? The depending on the deadline and the task characteristics, the priority should be fixed by the programmer. The operating system should not change the priority once it is assigned by the programmer. And the real time POSIX requires at least 32 priority levels, 32 real time priority levels, that is a requirement. There has to be absolute and relative timers, both types of timers have to be supported. Nano sleep function to provide high precision, so high precision timers with nano sleep function need to be provided, and virtual memory is supported, but need memory locking to lock a page. This is the name of the service. mlock is the service to be provided, which will lock a specific page, or mlock all will lock the entire address space, and munlock all, etc. Multi-threading support is required. Real-time POSIX and real-time file system with pre-allocated and contiguous files required. So, we had said that real-time files provide deterministic data access. So, for that we need to have contiguous file blocks in the disk and pre-allocated files. The scheduling policies that are mentioned in the POSIX 4 document, there are three main types. One is the sched FIFO. This is a fixed priority preemptive scheduling. We know all these terms, what it means. Fixed priority preemptive scheduling, using which we can implement RMA. Equal priority, if the tasks have equal priority, then they will be handled in a FIFO order. So, the sched FIFO provides fixed priority preemptive scheduling, and if tasks are assigned equal priorities, then they will be handled in FIFO order. Once a task completes, the other task will be taken up at that priority level. Then we have the policy sched round robin. So, this is similar to sched FIFO, fixed priority preemptive scheduling, except that for equal priority tasks they are handled in a round robin manner. So, sched FIFO and sched RR are both supported. One is equal priority. See, for other tasks these two are same, but only for equal priority tasks they differ, the sched FIFO and sched RR. And sched other is if the programmer needs specific scheduling policy to be used, he should be able to use it. Sched other is implementation of any specific scheduling policy required by the programmer. Now, the POSIX 4 also requires support for real time signals, but before we understand real time signals, let us see what is traditional signals and what is the shortcoming of this. Why isn't it useful for real time applications? In the traditional operating system, for example, the POSIX 1, which is the interface specification for traditional operating system, traditional Unix based operating systems, the signals are not queued, and as a result signals which occur before a signal is handled can get lost, and also signals are not prioritized. Obviously, they are not queued and therefore, they are not prioritized. So, once one signal is being handled, another signal will be ignored, and even if it is a higher priority, and events of same kind produce signal with the same number. This is also another characteristic of the traditional system. For example, if you press Ctrl D, right, the signal is the same, Ctrl Z or something. So, signals are similar, or a kill signal or something. In a real time signal, the signals have to be queued, so that events will not get lost, and the queued signals are handled in the priority order depending on the application generating the signal, and also these contain additional fields which are used to which can be used to exchange data. It is just not a signal, but also accompanying data. So, real time signals is a requirement in POSIX 4 and also the thread extensions. The POSIX 1 process model is not suitable for many real time applications, because processes have high context switch times, as some of you were mentioning. Not only the high context switch times, but many embedded applications, they cannot afford separate address spaces for processes, because even though the data being used by different processes is the same and the code is the same, they do not share it. Each one has its own address space, each process has its own address space. The code may be replicated. If two processes have the same code, the code is replicated. So, this is basically the situation in a single thread. The code, data, open files, register, stack are all private to a process and has one thread. On the other hand, in a multi-threaded process, we have the code, data and open files are shared among all processes. Just see here, these are all shared. What is not shared among threads is the registers and the stack. They have independent registers and stack, but the memory is basically shared. The code part, the data part and the open files are all shared among multiple threads. Know that for I think some of you already know, for a real time application, threads are beneficial. One is responsiveness, because threads share code and data. When you create a new thread, it takes very less time, because you do not have to copy all that code and data into the memory. The same data code that is available in the memory is being used. What is needed is the registers, right, and the stack. So, thread creation and switching is much more efficient. It is after all the same code and data is being used. So, creation and switching is very efficient. Just to give an example, in the Solaris operating system, creating a thread is 30 times less costly compared to a process creation, and context switch is about 5 times faster than a process. Three types of schedulers are supported in the POSIX 4. One is the global schedulers, and the other is local scheduler, and the last one is mixed scheduler. Three different types of schedulers can coexist in the operating system. In a global scheduler, when it is used, a thread competes with all other threads. Okay, thread is scheduled, is for the processor, it competes with all other threads. In a local scheduler, the thread competes only with other threads of the same process, whereas in a mixed scheduler, some threads can have global contention and others can have local. You can define this. You can define a global scheduling policy or a local scheduling policy or a mixed scheduler. So, that is another requirement for POSIX 4. It also, POSIX 4 supports sporadic servers. We had seen sporadic servers, isn't it? We had discussed. What is sporadic server? Do you remember?
Not periodic. It is to handle the sporadic. It regularly checks the event of task arrival. The time interval between two tasks arrival will not be equal for all. It can occur anyway.
No, that is a sporadic task. That what you are saying is the definition of a sporadic task where it is not periodic, right? It can occur in some statistical pattern. But what is a sporadic server? Anybody remembers what is?
Any sporadic tasks have arrived on,
And because of tickets, it will allow it to be scheduled.
Okay, you remember partly, but what is the full answer? Okay.
Every interval of time it will check the life period of the ticket, and then if it is used, then it will regenerate.
No, but for what purpose is it used?
To schedule the sporadic tasks. Sporadic and non-periodic.
Okay. Okay, see, it is used, the sporadic servers are used for scheduling sporadic tasks. See, one way the sporadic tasks can be handled is that if the CPU is unused for periodic tasks, like some of the periodic tasks did not occur, they did not use their slot, completed early, no tasks are getting executed. So, the lowest priority task can be the sporadic tasks. They just lap up the CPU time when no other task is ready to use. That is one way to implement, but at least the sporadic tasks execute at the lowest priority. But for many applications, the sporadic tasks need to also be operated on some priority, because there can be important sporadic events. For example, let us say a condition needing some attention, and that condition does not occur periodically, but it can occur once in a while, right. So, some sporadic tasks need to be operated at a priority level, but at the same time we will have to ensure that by giving a priority to a sporadic task, it does not really negatively influence the performance of the lower priority task. See, higher priority task it cannot influence, but just because it was given a priority, it should not suddenly some 10 sporadic tasks occurred in some statistical pattern and they just lapped up the CPU time, and the lower priority tasks they started missing their deadline. That should not occur. So, that is the main reason for the sporadic server, is that the sporadic tasks can operate in some priority level, but at the same time ensure that lower priority tasks are negatively affected when too many sporadic events occur. That is the main idea here. We had discussed about sporadic servers, if you can recollect the earlier discussions. So, these are used to process sporadic events at any desired priority level, and at the same time guaranteeing that lower priority tasks are not negatively affected when too many sporadic events occur. Is that okay? Okay. So, the sporadic servers need to also be supported under POSIX 4. So, let me just ask few questions. So, what is the main problem when Unix is used in real time application? What are the main problems that you will face if you attempt to use a Unix system in a real time application? Sorry? Resource sharing among real time tasks is a problem. What problem will it cause? Priority inversion. Okay. So, it can cause unbounded priority inversions in Unix among resources shared among real time tasks. Okay, that is one problem. What are the other problems?
No real time.
Okay, Unix does not have a real time priority support, all are dynamic priority levels. What else? Are there any other fundamental problems? It cannot be real time file support. You can add contiguous allocation or pre-allocation of blocks, that you can do.
In kernel mode, interrupts are disabled.
Okay, yeah, that is an important problem of Unix, that it is non-preemptable in the kernel mode. Once a user task makes a system call, becomes non-preemptable, and therefore, the response time for a critical event can be up to a second, can be more than a second also. So, those are the main problems of Unix. We have discussed about that. Okay, this we know what is a real time priority level static priority level and how it is different from the traditional priority level, we know that. Let me not. So, what is real time POSIX? Anybody like to answer different? What is real time POSIX?
Provides memory lock.
No, that is just one feature, but generally somebody asks you that, see, you have done this course, we heard this term real time POSIX. So, what do you mean? Your colleague in your company might ask you that, see, what is this real time POSIX? Can you just tell me?
Real time extensions to
Anybody else would like to answer this question?
supports real time task priority.
No, this is specific features. He is saying memory locking, you are saying task priority, real time priority, etc. These are specific features of the or specific requirement of the real time POSIX. But what is it? What is real time POSIX? Okay, it defines the basic services that need to be supported by an operating system to be real time POSIX compliant, or these are the features, standard features that are expected of a real time operating system. Now, do you remember the basic requirement? Some of you were saying about memory locking in a virtual memory system, is saying real time priority level. What are the other requirements for a real time POSIX? Remember any of the requirement of real time POSIX? Yes, two you had identified. He had identified memory locking support and he had identified real time priority levels, and 32 of them. Besides that, 32 priority levels, they were saying. Okay. Other than that, are there any other requirements of real time POSIX?
High precision is provided by nanosecond.
Okay. So, the timers, periodic and asynchronous timers, and periodic aperiodic timers, and then the nano sleep function, real time signals, real time files, and the different scheduling policies.
Then it can support all the static real time priorities.
Okay, that he has said already. Preemptive priority based scheduling policy and so on. Okay. So, how is a real time signal different from a traditional signal in operating system? Okay, events cannot get lost, this can have data associated with it, and they can have priorities. So, just tell me whether these statements are true or false. Now, as a programmer, you want to sample a sensor, a temperature sensor or a pressure sensor, something at regular intervals. So, would you use a real watchdog timer for this work? Yeah, this is false. Watchdog timer is a one-shot timer. For a periodic event, regular intervals, you need to use a periodic timer. POSIX is an attempt to provide portability of executable files across Unix platforms. What do you think? Is this true or false? False. So, what is true?
So it's an open standard for all the source code.
Yeah, the main focus of POSIX is to provide portability at the source code level, not at executable code level.
Sir?
Yes.
So, in that first question, so that sampling of that sensor.
Yeah.
So like so during implementation also we can, so given that the overhead of setting and resetting a work timer is like not much, can be ignored. So we can set and then reset and then again set a work timer, and that will also use it.
No, see, for a regular handling of an event, you just set a periodic timer, and watchdog timer, the purpose is different. Here you just time out and process. Okay. What about this statement? POSIX standard requires real-time processes to be scheduled at priorities higher than the kernel processes. Do you agree with this? POSIX standard requires real-time processes to be scheduled at priorities higher than the kernel processes. Okay, it provides real-time priority levels where you can make it operate higher than kernel processes, but it is not required to make it operate always higher than the kernel process. So, real-time processes to be scheduled, implicitly it says that always they are scheduled at priorities higher than the kernel process, which is false. Why threads are more suitable in real-time applications as compared to using processes? I think that you had answered that creation, context switches, etc. are faster. Now, let us look at how the Unix has been extended. We had seen the problems with Unix as far as real-time application development is concerned. So, let us see the different ways in which the vendors have extended Unix to make it work in a real time and in embedded application. So, several efforts have been reported. Some have reported implementing real time task scheduler, finer granularity timer, real time file system. This is some basic extensions to the Unix kernel, simple extensions. Some time back we were even giving this as project work for UG and PG students to provide certain facilities to Unix, add certain facilities to the Unix kernel, so that they support some specific features. But all these features, real time task scheduler, finer granular timer, real time file system, etc., they provide only minor relief, because the fundamental problems are there still. The non preemptable kernel, poor resource sharing support, and so on. Several operating system, open source as well as commercial operating system, have appeared which attempt to make Unix suitable for real time application. One is extensions to the Unix kernel, the host target approach using preemption points, and then the fully preemptable kernel. We will just look at these 4 types of approaches, and then we will look at specific operating systems. In the host target approach, the application is developed on a Unix host, of course, maybe non-Unix host also, and then the application is downloaded to a dedicated operating system running on the target, a very simple operating system. Basically runs the task rather than supporting development of the application. And the Unix host is connected to the target via a TCP/IP interface, where you download the application. Important examples are PSOS and VRTX, etc. So, this is the scenario in a host target approach. You have a processor card here, to be used in the embedded application. The processor, memory, etc. are here. The extension slots, and then this is the host running Unix or any other operating system, where you develop the application and then download it onto the RAM here, and then you test it. It provides several facilities for running the tasks on the board and test it. You can debug it also. So, here there is a component which sends the status of various components, and the data values can be monitored from the host. Once you are satisfied with the development, the software, you fuse it onto a flash memory or a ROM, and then this is used in the embedded application. So, the development environment is on the host, the target has only the running the execution environment. The target operating system is very small and fast. It need not support compilation, debugging, libraries, virtual memory. See, all these are development tools, right? You do not need to have a compiler, bulky software, debugging support, libraries, virtual memory support, etc. Because unless you run bulky applications like compilation, etc., you do not need virtual memory. For simple embedded applications, a host target approach is satisfactory, and the task preemption time is of the order of 10 microseconds compared to milliseconds, hundreds of milliseconds for Unix implementations. So, this is the scenario for the POSIX operating system. On the host side, you have the development tool, compilation tools, etc., and there is a component of the POSIX operating system called as X-ray, which helps you to download onto the target board and also help debug it. So, there is a POSIX network component here, and the target debugger, where you can set debugging commands from here and get the results. You can set breakpoints and so on. The host provides tools like cross compilers, libraries, editors, and other development tools, and you use the debugger on the host side to debug the target board, the application running on the target board. Once the application is developed, the tools that are there on the host are not necessary. You just once it is fully tested and debugged, you just fuse it on a ROM or a flash. There is another category of approaches. We will also look at this, examples of this, the preemption point approach. Here in the operating system code, the kernel code, at specific points, preemption points are introduced in the system calls. See, earlier in the traditional Unix, once the system call occurs, until the system call completes, it is not preemptible. But here, at the points where the kernel data structure is consistent, you can look for other tasks to run and can take up those tasks and suspend the task which was running. The system call that was running can be suspended and other tasks can be run. Some example of preemption point, HPUX is a popular example of the preemption point approach. And then we have the preemptable, fully preemptable kernel. we had said that for making the kernel fully preemptable need locking support, is not it? Because the traditional Unix there are no locking used for efficiency reasons, and the interrupt was disabled, is not it? So, there are two types of locks that are used. One is the kernel level locks, which are like traditional locks, but what about spin locks? Anybody heard about spin locks? Because these are also being used nowadays in traditional operating systems, especially the multiprocessor operating systems like multi-core or multiprocessor, they have to use spin locks. Anybody heard about spin locks? Okay, so let us discuss about spin locks, because these are even taught in a traditional operating system course. So, the idea behind spin lock is as follows. See, if a task, both the tasks T1 and T2 need certain shared resource. Okay. Now, T1 is acquired the resource, and using T1 is using the resource, and that time let us say T2 also requested the resource. Okay. Now, T2 waits for the resource, and by the Unix operating system semantics, as soon as the task waits for something, it gets preempted, is not it? It gets context switched. A waiting task is context switched, but just imagine that suppose the resource is needed here by T1 for doing some 1 or 2 instructions, let us say just increment a clock value or read a clock value or something. So, it has set the lock here for doing some simple operation 2-3 instructions on the resource, but by that time if the task T2 wanted the resource, then it will be context switched, because it has to wait for it and the Unix would context switch it, is not it? And context switching involves much more overhead, because all its the context needs to be saved, and again it needs to be restarted at a later time. But can't it just BG wait here without context switching? Can't it just keep on waiting here and then know that this is will be used only for 1 or 2 instructions, and as soon as this gets done with this, it can start using it. So, that is the main idea here. For small processing involving a resource, a spin lock is set. So, if you are a programmer and you are using a resource for 1 or 2 instructions, to lock it,
information about T1 that it is using resource for only this much.
That is the programmer. So, the programmer knows that what he is going to, once he locks the resource, what is he going to do, the code that he knows, right. So, if you are a programmer, you would know that once you lock the resource, how much processing you are going to do with the resource, right. So, if you know that you are just going to increment some value or do some simple operations, you will not set a kernel lock, you will set a spin lock, so that another task which is trying to access that resource will not context switch, it will just BG wait for that resource. So, a spin lock, use of a spin lock can result in faster completion time for tasks and avoid context switches. Is that okay? What is a spin lock? A spin lock is also a lock, but unlike the traditional locks, the spin lock is set for resources or set for processing, for very small processing when a resource is locked, and another process which needs that resource, if the spin lock is set, it will not context switch, it will just do a BG wait, and in any case the resource will be available within very short time, and therefore, it can continue without incurring a context switch. Okay, let us proceed. Now, Linux is also become extremely popular, as we were discussing. There are many approaches to make Linux real time, mainly two approaches. One is the preemption improvement, and the other is a fully preemptable kernel. Preemption improvement and fully preemptable kernel, unfortunately that is not showing there, written there interrupt abstraction, fully preemptable kernel. So, let us look at these two approaches. First, let us look at the preemption improvement. The code is modified so that the amount of time the kernel spends in the non-preemptable part is reduced. See here again, some part of the code it is non-preemptable, but that is reduced. The main strategy adopted is reduce the length of the longest section of the non-preemptable code, similar to the preemption point approach. Now, let us look at the interrupt abstraction approach. Instead of instrumenting the code to increase preemptability, that is reduce the sections of the code where it is prevented, the preemption is prevented, the entire kernel is made preemptable. How is that done? See here, a separate layer intercepts and manages the hardware interrupts. But how will that help? If a separate layer intercepting the interrupts and managing the interrupts, how will that help? How will that make the kernel fully preemptable? Yes, okay, let us proceed. Possibly this will become clearer, that we have the kernel itself becomes preemptable because there is a separate code, separate interrupt abstraction layer which is handling the interrupt, and the kernel is running as a task of this. We will see that. The hardware abstraction layer has the complete control over the interrupts, and the kernel actually runs as a task of this. The hardware abstraction layer has complete control over the hardware interrupts, and the Linux kernel runs as a task of the real time scheduler. Under the real time scheduler, the kernel runs as a task. One of the major problem with the preemption improvement model is that this, if you look at the literature on the real time operating system based on the preemption improvement model, you will see that it guarantees the longest measured interrupt latency. See, there is a catch here. The longest measured interrupt latency, it will say that, see, 100 millisecond or 50 millisecond is the longest measured interrupt latency, but there is a catch here, because it does not provide that it will never exceed that 50 millisecond. It says that it is the longest measured latency. If you find that something as 100 millisecond under some situation, they will say that that path was not measured. It is the measured interrupt latency, the paths that were measured. The meaning of this is that the paths that were measured, on that the longest interrupt latency was 50 millisecond. It does not provide guarantee about the latency, worst case latency. See, if it was the awarded as the worst case interrupt latency is something, then that guarantees, but here it is the longest measured interrupt latency. Highly misleading, but that is how it appears. So, because all paths cannot be measured, the code is complex. So, there is no guarantee given on every path, it is just whatever was the measured, on that the maximum value is reported. Now, let us look at the interrupt abstraction model. In the interrupt abstraction model, the Linux kernel basically is unmodified. The same Linux kernel runs, and the real time tasks run as kernel loadable modules. Okay. So, in the interrupt abstraction model, the Linux kernel runs unmodified, and the real time tasks, they run as kernel loadable module. So, they operate as a kernel task at the kernel level priority they operate. But the problem with the interrupt, we will see the interrupt abstraction model in more detail as we proceed. But let us remember the shortcoming of the interrupt abstraction model. The main problem is that the applications are becoming more and more complex, and we know that the key to build complex application is memory protection, resource management, process isolation. But here once they run in the kernel mode, those are not guaranteed. So, the debugging of the applications become extremely difficult in the interrupt abstraction model, because after all the applications run in the kernel mode. So, that is a problem with the interrupt abstraction model. But there has been attempts to overcome the limitations of the interrupt abstraction model, and the most important of that is the RTAI project. We will see the details of the RTAI project. It allows real time user space processes. So, the application is no more a kernel process, operate as user level processes. The RTAI stands for real time application interface. We will see that the RTLinux, we will see the features of RTLinux in more detail. This is actually an interrupt abstraction model, where the Linux kernel runs as a task of the real time scheduler at the lowest priority, and the application runs as a kernel task. If you think of it, the RTLinux and RTAI are quite similar. For both, the Linux kernel becomes a task of the real time scheduler. In RTAI, the real time tasks communicate with ordinary Linux processes through shared memory. We will see more details of RTAI, because this is a important initiative on the making Linux real time. And since these are free software, these are important for many types of embedded applications. So, here the changes to the Linux kernel is by adding a hardware abstraction layer, and in contrast the RTLinux applies changes to the kernel source files. So, first let us look at the RTLinux, and then we will examine the RTAI, so that the concepts will become clearer. So far we just said that, see, both are using a interrupt abstraction model, where an hardware abstraction layer is there, which hijacks the interrupts, and then it reports it to the real time task scheduler, and the Linux kernel actually runs as a task of the real time task scheduler. So, see here, if you have a Linux system, and you implement the RTLinux on it, then the RTLinux here or the RT kernel that is written here, the RTLinux, it will hijack the hardware from the Linux. See, it has come and sit between, the Linux and the hardware. So, the RT kernel or the RTLinux will intercept the hardware and attend to all hardware interrupts. And if an interrupt is to cause a real time task to run, then it will just interrupt the real time kernel. So, full preemptibility of the real time kernel, the Linux kernel is ensured here, because it is after all the RT kernel which is interrupting it, and then it allows the real time task to run. So, this uses a separate approach to make the Linux kernel fully preemptible. So, here the features of RTLinux is that different modules of the kernel can be selectively loaded. So, it can be easily tailored to fit into an available memory of an embedded application. Both fixed and dynamic priority levels are supported. Context switch is of the order of 15 microsecond. The biggest advantages here is that the source code is available, and when developing a software, an application, if you find that some specific driver or specific part of the kernel is causing undesirable delay, then you can even attempt to change the source code of the kernel. But if it is a commercial package, commercial operating system, you can't do that. If you find that a specific service is taking longer than what you need, you either use that or don't use that operating system, or you can at best request the vendor whether something can be done, but you have no control. But here you have control on the source code, and you can fine tune the source code. So, this is the way it works here. This is the traditional Linux kernel. In a traditional Linux kernel, we had discussed this model earlier also, the traditional Linux model, where the user processes, by invoking the system libraries, they avail of the services, and the interrupts are reported to the drivers, and the I/O is also performed by the device drivers, and the Linux kernel sits on top of the device drivers. But in the RTLinux, see here, the RTLinux has hijacked the hardware here from the Linux. The Linux has become a background task, a low priority task for the RTLinux kernel. Here, see here, the real time tasks are directly running on the real time scheduler, and the Linux is also running as a task of the real time scheduler, and it can, if a real time task becomes ready, it can interrupt the Linux kernel. Linux is the lowest priority real time task. So, the interrupts, if it is meant for the Linux kernel, they are reported here in forms of software interrupts, and for I/O the Linux requests the RTLinux here, whereas the real time tasks can have direct access to the hardware if necessary for faster I/O. See, they can also do I/O through the real time Linux, but some tasks are also allowed to have direct access to the hardware. So, we will stop here today. In the next class, we will look at the RTLinux in more detail, and we will look at the RTAI, which is an improvement, or some of the shortcomings of the RTLinux are attempted to be overcome in the RTAI. See, in the RTLinux we are saying that the real time tasks, they run in the kernel mode. This is possibly one of the major problems with the RTLinux based software development, debugging and development of the application becomes difficult. So, we will see how RTAI tries to overcome this problem. So, we will stop here today.